Okay, so in this video, I am going to explain few physical properties, very important physical properties, whatever we used in different purpose in different part of physics. So my main motivation to teach you those physical concepts in a very simple language. Okay, so today I am going to discuss or talk about Dirac-delta function. So maybe I can share the screen, okay, like this one. I hope you can see the screen. So let me take close screen. Okay. So all of us, it's like we know P, take a full form is, okay, who was a very famous British theoretical physicist, and he made a fundamental contribution to the early development of both quantum mechanics and quantum electrodynamics. So he had contribution both in quantum mechanics and quantum electrodynamics, QED. And he is known for very famous Dirac equation in quantum mechanics or in quantum field theory. So this is the equation for fermions, basically. And he also shared the Nobel Prize, the famous Nobel Prize, with Schrödinger. This is a well-known name to us in 1933. And he was introduced this Dirac delta function in the for mathematical formulation of quantum mechanics. So for us, the most important thing which you have to remember. So okay, we will discuss in details about Dirac delta function, but thing is, first we have to know the main contributor of the Dirac delta function. So Dirac in 1930, if I'm not wrong, or in that time when he was formulated the mathematical formulation for the quantum mechanics, then he was introduced this Dirac-delta function. So we will try to understand today about few basic concepts of Dirac-delta function and few important properties of Dirac-delta function. And I will try to prove few other properties, and I believe few other properties for you for your understanding. Okay, the first thing is, let me, so the we consider about delta x. So this is we call it a Dirac delta function. In the year 1930, Paul Dirac was introduced this Dirac delta function when he was formalized the quantum mechanics. And this Dirac delta function is a mathematical function which had a many useful, which is basically a useful tool in physics or in quantum mechanics or quantum field theory. So in many places, we very frequently deal with Dirac-delta function. That's why I think in the first lecture, I want to discuss about Dirac-delta function. Okay, so let me define Dirac-delta function first in some defined way. So as I already told you, my motivation is to teach you few physical properties in a simple language. I don't want to, for this basic course, I don't want to go in details. So in the next, maybe in next, I'll be take one more lectures on Dirac-delta function, where I'll be give you more advanced aspect of Dirac-delta function. Okay, so let's consider a function f of x. Okay, so this f of x is a well-defined function. Let's consider at x equals to x naught. So I consider a function f of x, which is a well-defined function at x equals to x naught. Now I am going to define a function in such a way that I will later prove this one, but not for now. Now we use this as a tool. From minus infinity to plus infinity, I define a function delta of x minus x naught, f of x dx. So when we try to calculate this integral value, so this will be contribute like f of x naught, and then I can define this delta of x minus x naught dx. And then I can write this one like f of x naught. So what is implied? It's implied. Let me take this one. Okay. So here I define a function delta of x minus x naught, which has a sharp peak at x equals to x naught. What that mean? So I want to imply. So I said ki delta of x minus x naught. This function has a certain property. So is that so when, so maybe I can define like this: at x not equals to x naught. So if the value of x, the variable is not x naught, is slight difference, like your your x is equals to x naught plus minus some small epsilon, or in other range, at x equals to x naught, this function I can, this function will be suppose 0. At x equals to x naught, not equal, but this will be something like infinity at x equals to x naught. Not only that, see here at this point, at this point I consider this basically equals to 1. Okay, so I can define this like this also. So, and let me take the red color. Okay, so I define integration from minus infinity to plus infinity delta of x minus x naught, that equals to 1. So this is the basic definition of Dirac-delta function. So now at this moment, so this is a mathematical tool for us, which I am going to use this property. Now in the advanced video, I will discuss why this thing is true. Okay, but for now, I consider this is the basic standard, basic, this is the base of my today's talk, today's lecture. Okay, so you have to now keep in mind, whenever we're talking about the Dirac-delta function, so this function has some certain properties, and this is the properties of this function. Okay, good. Now I am going to discuss few important properties of Dirac-delta function. Let me write properties of Dirac-delta function. Okay, so let me prove the first property. Let me write the first property which I'm going to prove is, let's try to understand, try to prove what whether it is true or not. Okay, so this is a very important important properties of delta function. We will be used frequently this property in many part of physics. Okay, let me try to prove this one first. So how can I prove this one? Let me take the black one. So I can define a integral I1, and let me define the integral like this: minus infinity to plus infinity delta of x f of x. I already defined what is f of x. F of x is a function, well-defined function at s equals to x naught, and dx. Okay, so what will we expect? So this should be, I can write this in like this also: delta of x minus 0 f of x dx. So this will be f of 0 from minus infinity to plus infinity delta of x dx. This is actually x minus 1, x minus 0. And as I already proved this one, I said this is not proof. I already told you this will be 1, this quantity will be 1. I will prove later. This will be f of 0. Okay. Now, if we consider, so this is one of the integration I write. The next one I want to write. So what will be happen if we change my variable? If I change my variable x to minus x, so this will give you dy equals to minus dx, right? So if I want to write the integration value once again in another, so our previous integration was from minus infinity to plus infinity, then right, from minus infinity to plus infinity delta of, let I want to calculate this one. Okay, so now if I want to change the variable y to minus y, so this will be what if, so this will be plus infinity to minus infinity delta of y f of minus y with a minus sign, let me write here only, minus dy. Am I right? Again, we can write this one, you can change the minus sign and this limit will be changed. So it will be minus infinity to plus infinity delta of y f of minus y d of y, which is nothing but f of 0, which we can write also from minus infinity to plus infinity delta of x f of x dx. Okay, so if we go it up, so see here when I define this I1 function, so it was minus infinity plus infinity delta f of x dx. So I get f of naught or f of 0. I get the same thing from here also. So we can write, so first one I try to explain in a more details way: minus infinity to plus infinity delta of minus x f of x dx equals to minus infinity plus infinity delta of x f of x dx. So here we want to use a very useful trick of mathematics, like this to integral is equal in for all possible value of x. ranging from minus infinity to plus infinity. As their integral value is equal, so the integrand that should be equal. So we can write, delta of minus x equals to delta x. So next, whatever the properties I am going to prove, all are using the same concept. So this one, that's why I discuss one of the properties in a details way, and let's try to check other properties of Dirac-delta function. So let me write, this is the our first property we define or we derive or we proved. Let me show you another properties of Dirac-delta function. It is a very important properties of Dirac-delta function. Let me use the green color. And the second property I'm going to show, delta of ax equals to 1 by mod of a delta of x. Okay, this is very useful. This one actually, this property of delta function is very useful. We use in many different part in quantum mechanics. How we can prove this one? Okay, so any guess? So for to prove this one, okay, let me first take black colors. So we will prove this problem in it for two different cases. In case one, when our a is greater than 0, we consider a is positive. For this case, I can define one integration from minus infinity to plus infinity delta of x f of x dx. Okay. Now, if I want to change the variable, okay, I can. So this is a basic fundamental recipe to prove this one. Okay, whenever we try to prove this, we use the same recipe. So dy is equals to a dx. Okay, so just for dy over a. Okay. So how can I prove? Okay. So I want to change the limit. Is it positive? The limit will remain same. It will be delta of y, and it will be f of x will be y over a, dx will be dy over a. So a is positive here, so I can take out. So that's why I'm talking about is positive. Next step I also what will happen if a is negative. Okay. Delta of y, f of y over a, d of a. So this is nothing but 1 over a, f of 0. So we can define this like 1 over a from minus infinity to plus infinity delta of x f of x dx. So let me note this one. Okay. Now I want to see the another properties, like what will be happen if your a is negative. So from here, what can I say? So if I go up, so if we're going up, so here from I can define. So I can say delta of ax that equals to 1 over a delta of x. Am I right? So now let me go to the next page. And I want to see what will happen when a is negative, a less than 0. Okay. So then Again, I can write the integration value like I2 from minus infinity to plus infinity delta of ax f of x dx, but here your a is negative, so whenever we want to transfer y equals to ax, okay, so this will be dy equals to a dx, but here a is negative, okay, so that's why whenever I will change this one, so there will be one contribution of this limit because a is negative, so this limit will be changed. So when I want to substitute this value here, it will be plus infinity, it will minus infinity, okay, delta of y f of, so x will be y over a and dx will be dy over n. So this is basically from I, if I change the limit, so 1 minus 1 will come here, and a is, I take the a out here, okay. So again, ultimately this will be f of 0, and this term I can write again. So the final answer, the final thing I can write like from minus infinity to plus infinity delta of x f of x dx. Okay. So okay. So from this point, I get delta of a of x when a is negative. I get from minus 1 over a delta of x. So this is one of the result I got. And if you see earlier, I got one more result here. So let me mark this with pink color. So when your a is positive, I got this relation. So here your a is positive. Okay. Now I what I got here, when a is negative, I got this result. So if I want to combine these two results, so I can say delta of ax that equals to 1 over a delta of x. So this is another important uh, properties of Dirac-delta function. Great. Okay, so if I want to prove one more properties of Dirac-delta function, which is very simple and very easy to prove. Let me take the green color. What is the green color? So third property, you can. This is very easy to prove. It is x delta of x equals to 0. Can you try to prove this one? It's very easy. Okay, what you have to do? The same recipe. I1 minus infinity to plus infinity x delta x f of x dx. So at x equals to 0, this should be equals to 0. So this function is defined at x equals to x. So this function not equals to 0. So that means this quantity is should be 0. So this is also proved. Also you can prove another. Okay. Now so there is another important identity which I am going to define now. I am not going to prove this identity, but I want to use this identity. So this will be the fifth one. So in next future video, I'll be derive this formula also. So I define one functional. So function of function that consider like So I consider function g of x. So this now here it is a functional, and this will be, this I can define like, I am not going to prove at this moment, but definitely I'll do in future. But for now, I'll be use this as a tool. Okay. What is this g? So g of x equals to e0. If I consider the equation, so this equation suppose had few roots like x of n. So where xn are the root of the equation. Okay. So let me take blue, black. So let, if I want to derive one very important physical identity, a mathematical identity of Dirac-delta function, that is equals to delta of x minus a into x minus b. What this identity? Let's suppose we don't know, we want to calculate. Okay. Let me take the blue dimension. So here, if we want to use a previous formula, then our g of x, that equals to x minus a into x minus b, which is nothing but x square minus ax minus bx plus ab. Okay, so g prime of x, that it will be twice of x minus a minus b. And we know from this equation, if I want to calculate the root of this equation, let me just write this one. So what is the root of this equation? G of x equals to 0. So obviously either x will be a or x will be b. So this equation has two roots. So now we want to calculate what will be the value of this quantity, x minus a into x minus b, right? So this will be according to the formula. If you go up, what? Okay, let me write the formula first. Once again. Okay, let me use this. So if I want to write the formula once again, our formula was delta of g of x, that was 1 over g prime xn delta of x minus xn. So, okay. So this was a formula we want to implement here. Okay. So let me. All right. Okay. So this should be, so what will happen when I put the value of A and B here? When I put the value of A in this formula, so like let me write somewhere here. So G prime of A, suppose if I put, so it will be twice of, so it will be minus of A minus B, right? So minus of A, so this will be 2A, so it will be A minus B. And what will be happen when I calculate this? So it will 2B minus A minus B. So it will be B minus A, so it will be A minus B. So this thing in combine we can write, right? A minus B, then delta of x minus A plus delta of x minus B. So this is a very important formula we sometimes use in our in a Dirac-delta function in many different purposes in physics. Okay. So now I can give you some homework, which will be again in the same way you can prove. So you can show that delta of square root of x minus square root of a, that equals to the exact in the same way, delta of x minus a. Or you can prove delta of square root of x minus a, that equals to 0. Okay. Or you can prove delta of square root of x square minus a square, that equals to 0. So this 3 will be your homework. Okay. So in the next video, I'll be discuss some properties of Dirac-delta function, how we derive, how we do the derivative of the Dirac-delta function, and I'll be discuss few properties of derivative of Dirac-delta function. So what we learned today, let me summarize. So summary. I like to write summary using it. So in the very first thing we learned today, how we define Dirac-delta function. Okay, delta of x minus x naught, that equals to 0 if your x not equals to x naught, and this equals to infinity if x equals to x naught, and also from minus infinity to plus infinity, delta of x minus x naught, that equals to 1. This is one thing we learn. So whenever we talk about the Dirac-delta function, this is the first thing it will become in your mind, right? So this thing you have to always keep in mind. So mathematically, Dirac-delta function means this. Okay. Now in next video, I'll be explain you how Dirac-delta function is came in the picture of quantum mechanics when Dirac interpret this one, and in what physical purpose we use Dirac-delta function. Great. The next thing what we learn today, few properties of Dirac-delta function. The second thing, what we learn? We learn delta of minus x, that equals to delta of x. Yes or no? We learn this one. Great. We learn delta of ax equals to 1 by mod of a. delta of x. If you do this one, okay. Then fourth one, what we saw, delta of g of x, which is the most important properties of Dirac-delta function, g prime of x n, yeah, delta of x minus xn. Okay, where xn is the, okay, you write where xn are roots of g of x equals to 0. Okay, so these four things, whatever we discuss or learn today, and the next video I'll be explain you few more properties of Dirac-delta function, and then I will show you in a details way in what physical context we use Dirac-delta function. So I hope you learned something new, and if you have any doubt, feel free to ask me. And our main motive to teach you or to explain you few physical concept in a very simple language. I'm not going in details in any one of the step, and my main motivation was to make you understand the very simple property or simple things, but which is very interesting in many different contexts in physics. So see you in the next video.